What we were talking about last time is the general theory of space-based representations and quasi-probability distributions and their applications to quantum optics. And one of the reasons for pursuing this is to better understand in what sense certain phenomena are essentially classical in nature, and in one sense they're essentially quantum mechanical in nature. Now, you may say, well, who cares? It is what it is. I mean, there is the full quantum theory, and it tells us what to do. It gives us recipes, if you like, for how to make predictions and make calculations, whether or not there is an equivalent classical description of the same phenomenon. Fair enough. You know, at some level, we might just be interested to understand, you know, in what way quantum mechanics is different from classical physics. But I think beyond that, what has become apparent in recent decades is that the distinctions between the behavior of quantum systems that have no classical analog whatsoever are actually a resource for doing things that are impossible in principle classically with sort of equivalent amount of resources. That's the whole business of quantum information, which we will come to hopefully in the last part of the semester. And so understanding at some level what aspects of the physics we're seeing are essentially classical in nature or essentially quantum in nature gives us a little sense of what sense is a certain, for example, light field a resource for doing quantum communication, a communication task that we wouldn't be able to do with a classical field. So that's another reason for pursuing this analysis. All right? So, you know, we have seen for many months now that, you know, we have made this categorization, put a boundary between the classical and the quantum by thinking about whether or not there was a classical probabilistic description of a certain phenomenon, and for example, photon counting. So we can look at photon counting and ask whether there's basically we can treat the field essentially classically. That is, and what I mean by essentially classically, meaning there is a classical probability distribution that describes the predictions of what we'd see in a particular experiment. And so in the context of photon counting, the appropriate distribution to consider to decide which side of the fence the state sits on was the Glauber Sudarshan P representation. Okay, because we've seen that if we have some normally ordered product of creation-annihilation operators and we looked at the expectation value, that expectation value was given by a kind of classical statistical average if this function P is a classical statistical function. Okay? So but what we're now seeing is that that's not really the whole story. It's not just about photon counting. We can probe the field in different ways. We can probe the field by looking at its quadratures through a homodyne measurement. And when we look at moments of quadratures, things like, you know, polynomials in the quadratures, then it's not about normally ordered products anymore. It's about symmetrically ordered products. So given that we wanted that motivation, we're sort of stepping back now and saying, well, let's think about just the general formulation of quantum theory when we're talking about a Hilbert space associated with an infinite dimensional Hilbert space, the sort of basic Hilbert space that you first learn about, kind of the most complicated one, but it's sort of usually what we learn about first when we talk about wave mechanics. And so we want to think about formulating quantum mechanics on phase space. Okay? And so we take our cue from the classical description, or a way of formulating the classical description on phase space in a classical statistical theory. So instead of having a point in phase space, we have some probability distribution on phase space. And that probability distribution of phase space is a representation of our lack of knowledge about where a part of what its momentum and or position are. And that distribution function is a probability function which evolves in time according to Hamiltonian dynamics. And that is what is sometimes called the Liouville equation. So this squiggly thing is the Poisson bracket. We'll come back to that in some weeks, thinking about the equivalent thereof in the quantum world. And so given this is the state of the system, classically, and it evolves, and we could then, for example, ask about, we can make predictions about what we'll do when we measure the system, what position and momentum will we find if we try to measure the particle in some way. And we, for example, can ask about what's the average value of some observable, which is a function of x and p. And that is then just the average of that observable, like the energy or the angular momentum or what have you, over the distribution function. Okay? And so what we seek in our quantum description is a representation like this, such that if I have some operator, which is a function of x and p observables, and I wanted to, for example, ask what is the expected value of that at some time t, then what I want is this to equal that. Okay? And of course, we do that all the time in either x or p, where this would be then the square of the wave function in either position space or momentum space. But x and p is a little different because, of course, the whole point is that x and p don't commute. So what's in particularly true is in the quantum theory, these guys are not unique. There's an uncountably infinite number of ways to do this, as we'll see in a moment. And the choice we make will be tied to the physics of the situation at hand. For example, are we doing photon counting? Are we doing moment measurement? Are we doing something else? Okay? So that's where we were, and that's where we're going. So, let's get there. All right, so this lecture is going to be somewhat mathematical. It's perhaps going to be pretty dry, depending upon who you are. There's just a certain amount. I've never found a way to kind of get this about. There's just math that needs to be done in order to get at the stuff we're going to be talking about. So, fair warning, all right? Now, so why is there an issue? What's the problem? Well, the problem is non-commutativity of X and P. Okay? So what that means is that if I have, let's just say I have some function that's a function of X and P. Sorry. The operators. What I mean is, let's say that function is X plus P squared. Well, so that function is X squared plus P squared plus X times P plus P times X, for example. So the way I've written this is explicitly symmetrically ordered. That's to say, there's every term that has an X on the left and a P on the right, there's another term with equal weighting that has them in the opposite order. Okay? Of course, I could commute things around and write it in a slightly different manner. I can write this as X squared plus P squared plus 2XP minus I. Right? I could do that. Those two things are equal. Or I could write it as X squared plus P squared plus 2PX plus I. All of those are equal, right? But if I can call, what I could see here is that if I make the assignment, of X becomes replaced by the variable X, and the operator P gets replaced by the C number P. There are sort of three different functions that I might associate with this operator. So there are three functions of X and P, C numbers, associated with these three orderings. So whereas all these operators are equal, the three functions of them I'm about to write down are not equal. So I can write down, I'll call it F0 is equal to X squared plus P squared plus 2XP. F plus 1 is X squared plus P squared plus 2XP minus I. And F minus 1 is X squared plus P squared plus 2XP plus I. Those are three functions that I obtain by looking at these three operators and making the substitution of X hat goes to the variable X, P hat goes to the variable P. Okay? So whereas these three operators are equal, these three functions are not. Okay? So there are three different representations in phase space of this operator, A. These are three different representations of that in phase space, depending upon how I chose to order X and P. If I chose it in the symmetric order and made the substitution, I got this. If I made the ordering with the X's on the left, I got this function. If I made the ordering with the X's on the right, I got that function. So there are three different representations. Okay, so it's clear there's not a unique representation of this operator in X and P because it depended how I chose to order it. All right. So, right. So, in order to deal with this, there's a whole theory about operator ordering in phase space, and it's convenient, instead of working with X and P, to work with alpha and alpha, or A and A dagger. Okay, which is more convenient. All right. So, I've considered some function. Again, for the moment, we're just considering one mode. If I have multi-modes, it doesn't make a difference. It's just a tensor product of different functions for each mode. And so I'll just focus here on a single mode, a particle, equivalent to a particle moving in one dimension. Okay? So here's some arbitrary function of A and A dagger. And let's say that I can write this as a convergent power series. We'll explain what that means in a moment. And I'm going to write this in different ways. On the Cn plus 1, A dagger to the n, A to the m. Or, equivalently, if I ordered it Cn m minus 1, A and A dagger to the m. Or, n equals 0 to infinity, Cn m 0, something I'm going to call the symmetric ordering of this. So, what have I done? Well, what I've done is said, let's imagine that I can express whatever this function is as a power series. And a power series with coefficients out front. And those coefficients out front depend on how I order A dagger relative to A. If I put all the A daggers on the left and all the A's on the right, this is the normally ordered. Okay? So there's a particular set of coefficients associated with whatever the function is after I've done all the commutators, whatever it is, in the same way like I just did it there with X and P. Now I do it here with A and A dagger, and whatever coefficients are left up front, I call them the C1s. Or I would, do the tedious A's and A daggers and put them in the other direction, and then, whatever coefficients are out there, I call them the C minus ones. And if this is the symmetric ordering, right? So this is all permutations. Normal and then normalized. So for example, A dagger A symmetrized is A dagger A plus A dagger over 2. Okay? And I can do that in principle. Okay? So, for the particular case where this operator is the density operator. Oh, before I say that, I guess I should say one other thing, which is that, okay, given these coefficients, which depend on the operator, I can define functions on phase space. Okay, so we define different phase space representations of the function, right? This is some operator A. On phase space. I will define F0, which is a function of alpha and alpha star, which is just take this set of coefficients and just substitute where I saw an A dagger, an alpha star, where I had an A alpha. At that point, everything commutes. So this is then the sum n equals 0 to infinity. Whatever those coefficients were, C n 0 alpha to the n, or sorry, alpha star to the n, alpha to the n. And similarly, I can have a 1 and a -1. Okay? So there are 3 different functions that I've written down here, depending on these 3 coefficients, 3 sets of coefficients, depending upon the original operator ordering that I was able to do. Yep.
So the one that you have written down there, is that the C1?
No,
Or
it's the C0.
oh, because now that they're just variables, it doesn't matter what order you
Exactly.
write them in. Okay.
Exactly. Good point. Thanks for emphasizing that. So once I wrote the operator A, substituted it with so let's look at this, make that substitution, right? This becomes alpha star alpha plus alpha alpha star over 2, which is just alpha star alpha. Okay? So what is different about these 3 functions, let me write it out explicitly just to emphasize that fact. So this is what I'm calling the function f plus 1 and f minus 1. What's different about these functions are these 3 sets of coefficients, okay? And those are determined from whatever the operators are. You have to write it in the operator ordering, then find those coefficients. Yes?
So these 3 are a subset of some very large number of...
Uncountably infinite.
Uncountably infinite numbers.
Yes.
Because I can make up whatever rule I want with the operator.
Right. So we're going to talk about the continuum of possibilities in a moment. These are the 3 that are most natural for reasons we'll explain in a moment. Now, when in the particular case where A is the state of the system quantum mechanically, the density matrix, or the density operator, then these functions are the representations of the state in phase space. That's what we want. Okay? And they have names. George, Reno, no, I did just watch the 1964, it was pretty, I was kind of bummed because John Lennon was, he was like doing nothing. It was all Paul McCartney all the time. Anyway. But,
Class movie for next time.
right. Okay, so when that's the case, these functions have names. And they're not George, Paul, Ringo. They're the Wigner function, the Husmi function, and the Glauber P function. So in particular, so let me just define, we'll just generally define F sigma of alpha. I'm sorry if my alphas look like sigmas, or when sigmas look like alphas, but so we define a distribution function, which I'll generally call W, function of alpha and alpha star, which is the representation of the density matrix, or the density operator with respect to that operator. And by convention, for reasons that we'll explain in a minute, we typically just normalize it that way. Okay? So, when sigma is 0, we actually usually don't write the 0 in there. We just call that W. And that's what's known as the Wigner function. When sigma is plus 1, this thing is called typically Q. And that is the Husmi function. And when sigma is minus 1, W of minus 1 is P, the Glauber P function. I'm sorry, Dr. Schiff, I just something that ran back. Okay, so those are what those functions are. We're going to, in a moment, what we're going to work on today is how do we calculate these things? How do we actually find them? And then we'll come today, or maybe a little bit later, to try to study what do they mean. Okay. All right. So, how are we going to find these coefficients, which is what we need effectively? I mean, in principle, we could do this with the A's and A daggers, right? I mean, whatever the function is, write it out in some polynomial and commute all the A daggers, commute all the, and yeah. No, we're not going to do that. So there's a whole theory of this, and it was developed in someone's PhD thesis, someone who we all know very well. Does anyone know who did that for their PhD thesis?
Kevin Cahill?
Kevin Cahill.
Wow, that's just a guess.
Really? Well, that's an excellent guess. Your spidey sense was right on. So, yes, there is a very famous paper. In fact, our podium speaker last week met with Kevin, and he said, "Why do I know that name Cahill? Not me." He said, "Why do you know that name? Because there's this famous paper by Cahill and Glauber." You didn't know that, right? That Kevin Cahill was Roy Glauber's student. Maybe you knew that, but he hasn't done quantum optics in 40 years, maybe. Anyway, I was looking for the reference to write it down for you guys, though. I'm missing something here, pardon me. Yeah. So. So this was in physical review before there was an A, B, C, or D, or LET, or anything else. It was just the physical review in 1969. Summer of Love, that's when it happened. All right. So, how are we going to deal with this? Well, the way we deal with it is through some very, very beautiful theory that we know that really, at some level, comes from the classical theory of distribution functions. But we need a little bit of foundation first. So, consider the following. So let's look at our friend, the displacement operator. Now, I should say, I'm going to go kind of back and forth whether I explicitly write that the operator is an explicit function of two variables, alpha and alpha star, x and p, or whether I just say it's a function of alpha. And notice that actually there are two variables here in this complex number. So this operator is this. So this is a kind of plain wavy-like thing. Okay. Now, notice that this operator, if I write it out explicitly, is a power series. Right? And this power series is symmetrically ordered. There's no special choice of whether A or A dagger is on the left or the right. So this operator, it gives me, as it stands, the symmetric ordering. Let me make sure all these little beeping things go. A dagger. Right. A dagger to the N, A to the M. There's a minus sign in there. Symmetrically ordered. Okay. So this particular operator, we can see what its coefficients are in the symmetric order. These are the C and M zeros associated with that operator. Okay. Now, if I wanted to find out what are the C plus ones associated with normally ordering this operator, it's generally a tedious thing to do. However, we can do it quickly, super duper quickly, because of our friend the Baker-Campbell-Hausdorff theorem. So note. Now, here's one point I want to emphasize, because it is always confusing, at least in my experience. The difference between the symbol, the normally ordered representation of an operator, or just taking an operator and normally ordering it, and the normally ordered series. Let me explain what I'm trying to say. What is this? Well, the symbol with the two dots on each side, the one that we saw before, is the thing that says, close your eyes, pretend everything commutes, and just move it wherever you feel like. Okay? That's what the dots mean. So this is equal to, well, in that case, it doesn't matter. I can put it like that. Is that clear? I didn't commute anything. All I did was I said, forget about the fact that they don't commute. If they don't commute, that could, you know, e to the a plus b is e to the a times e to the b. I can put them in any order I like, so I'm going to put them in normal order. So that's what the double dot symbol means. Okay, but that's not what we really want. We want the operator after we've done all the commutings. Okay? Now, by the Baker-Campbell-Hausdorff theorem, we know this is true. Okay? So the symmetrically ordered thing, so this is symmetrically ordered already, is equal to e to the minus alpha squared over 2 times the normally ordered guy. Okay? So this is the full operator, D. And this is what you get. When you do all those commutators, that's what you got left over. Is that clear? So, now what is this? Well, this is equal to the sum over n, I mean 0 to infinity, alpha to the n over n factorial a dagger to the n times n equals 0 to infinity alpha star with a minus sign to the power n factorial a to the n. Right? So that means that so that means the following. For this, those are the C zeros. If I write this out now, and infinity, yeah, actually what I want to say is the following. So what that says is that the normally ordered D is equal to e to the plus alpha squared over 2, the symmetrically ordered. And we know how to then get those coefficients. Similar, I'm going to define a perverse notation that no one has ever used other than me, but I like it. And that's the anti-normally ordered situation. Okay? And that means close your eyes, no cheating. And let it pretend everything commutes. They commute, move all the A's to the left, move all the A daggers to the right. Okay? So that's equal to e to the minus alpha star A e to the alpha A dagger. Okay. Which also has an obvious, this particular operator, this thing, this guy, you know, had this as its operator product. Right? And moreover, the symmetrically ordered guy, if I did Baker, Campbell, Hausdorff in the other order, you would find this. So that says that this guy over here is e to the minus alpha squared over 2 times the symmetrically ordered guy. Okay? This is this, and that is that. And now I come to your question, Steve, about the continuum of infinite possibilities. That's you. So now I can define, I'm going to define the sigma ordering of D. So D sigma, if I put alpha, is going to be defined as e to the sigma alpha squared over 2 times D. Where sigma equals 0 is symmetric. Sigma equals plus 1, according to what we have over there. This is the normal order. And sigma equals minus 1 is anti-normal order. Okay? So what that says is if I want to get, for this particular operator, which has this nice kind of polynomial form, I can write it automatically in a continuum of orders, ranging from ranging from normal to anti-normal with symmetric in between, and all sigmas in principle otherwise. Okay? So this is a piece of mathematics. It's just fact, right? You can see that it's really just followed from Baker, Campbell, Hausdorff. So why? So this kind of power series is going to be quite useful to us in order to define the operator ordering representations of the density matrix. How? Well, in order to do that, I need to step back a moment and talk about another thing in classical distribution theory. Okay? So to get at P, Q, and W, consider classical distributions. So in particular, what I want to talk about is something called the characteristic function. What do I mean by that? Well, so let's just start with a classical distribution on of one random variable. Okay, so it's just some classical probability where this is a continuous on the real line from minus infinity to infinity. Okay? So this is my distribution. My probability distribution. The characteristic function, which is often called chi, not to be confused with x, is the Fourier transform of the probability distribution. So this is not a function of x. This is a function of y. Integral over x, either minus I y times x, the probability distribution for x. So this function is also characterizes everything, every prediction we want, because of course if we know the Fourier transform of the probability distribution, then we have the distribution as well. But it's a very useful object. It's useful both from a calculational standpoint and also from the point of view of getting at the quantum distributions. In particular, we care often about the characteristic function because it enables us to calculate expected values of polynomials easily, in particular moments of the distribution. So the characteristic function is useful for calculating moments. So for example, suppose I want to look at the expected value of x to the n. X is a random variable. This is equal to the integral over the measure x to the n, the probability distribution over x, by definition, right? But a little tricky trick here says that what I can do, since this is kind of a generating, an exponential function is a generating function for all polynomials, because if I did a power series, this I have all the polynomials, then I can quickly get this by looking at the derivative, the nth power of the derivative of the characteristic function with respect to its variable. And then just evaluating that at y equals 0. Right? If I look at that, I take the derivative inside the exponent, because only this depends on y, and then I have this minus of I plus I to the power n. You buy it? Right? So that's quite useful. And we're going to use it in the future, but it's also going to be useful for us in terms of defining our representations of the quantum state in terms of in terms of something.
That's how I would say it, sorry.
I should say I can expand this to the multivariate case. So I could have a probability distribution for many variables. So that P is a function of the vector of variables. And then I can look at an arbitrary moment of some product of the random variables. And again, that's given by derivatives of the characteristic function evaluated at the origin. So in particular, this is the partial derivative with respect to I y1 and 1 times the partial derivative with respect to I y2 and 2 times dot 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 the partial derivative and nth variable on the y sub n to the n sub n, the characteristic function evaluated at the origin. Okay. So if I have the characteristic function, I can calculate any moment of the distribution, and that completely defines the distribution, of course. And of course, you can kind of see how that might be coming to our thing, because of course here we're looking at kind of moments of a dagger when we get these power series. So it's kind of coming back around to that. Okay, so with that said, we can define the characteristic function for the quantum state instead of for the classical distribution. Okay? So, again, D is like something that's kind of plane wavy. Right? So, a natural way of defining a characteristic function on phase space, where x and p are now like my random variables, is to define the characteristic function associated with the state rho as follows. Chi as a function of x and p is equal to the expected value of D. Why is that? Well, let's look back over here. Remember, I'm sorry I erased it. Chi for the classical distribution was this. What is that? That's nothing more than the expected value of this. That's what that is. I'm integrating this guy over the probability distribution. So the Fourier transform of the probability distribution is nothing more than the expected value of a plane wave. So we define equivalently the quantum version of that, which is just equal then to the trace of rho with the displacement operator. Moreover, we have automatically a way of deciding what the operator ordering is, because we have operator ordered values for these guys. We just wrote them down. So I could define a characteristic function associated with the particular operator ordering by just choosing the particular ordering of D. And then I've done it. And what we're going to show is that the quasi-probability distribution then is just the Fourier transform of this. So the x prime dt prime chi is a function of its dummy variables, e to the I x prime p minus p prime x. And I have two pi's around. The pi's in this whole business are enough to drive you completely bonkers. But the way that this is defined is this is. Yes, sir.
So the expectation value of the displacement operator
Yes.
changes based on how you write the displacement operator.
Right. So there is these are different operators. These are not all the same operators. These are different operators. So we had that D0 was either the alpha A dagger minus alpha star A. D plus 1 is alpha A dagger minus alpha star A. B minus 1
Yeah, I think so.
is the other way around. These are three different operators. Okay? They're three different operators, not equal. I can relate them to one another through that e to the sigma alpha squared, blah, 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 but these are three different operators. And thus, these are three different expectation values, and therefore, these are three different functions. And often, as I say, we write this in the complex representation and say chi sigma of alpha is equal to the trace of rho with d sigma of alpha. And the quasi-probability distribution is the integral then e squared over pi squared. And that is chi of alpha. Oh, I guess I should call this some other label. Beta. And then that thing becomes alpha beta star minus alpha star beta, where alpha is equal to x plus ip over root 2, and beta is x prime plus I b prime over root 2. This is where the root 2's really come in handy, otherwise it's a pain in the ass. So that's why at the end of the day, it's better to keep the root 2's in there. Okay, so this is something that you have to get used to, is dealing with Fourier transforms in phase space. This factor is pure imaginary up top because it's something minus the complex conjugate. So it's like a phase. So when we're dealing with x and p, we deal with alpha and alpha star, and this is the phase factor. Comes out there all the time. All right. So, so now, ultimately, we want to use these things to calculate expectation values and make predictions. So, I should say, as we're going to see in homework, often this is actually how you calculate things like the Wigner function. What you do is you take the trace of the state with the displacement operator. That gives you the characteristic function associated with the Wigner function. And then you take its inverse Fourier transform. We're going to do those. We need you, I guess me too, because I have to do the problems again to try to get them right for homework. Okay? All right, now, continuing, everyone take a drink because I know it's dry, but we got some more to do on this. So there's more that's related. There's a whole set of what I think is quite beautiful mathematics that we're kind of familiar with in the context of classical theory of Fourier analysis that now translates into this operator domain. Okay? So we want to, what we're kind of doing here is Fourier analysis of operators. That's what we're doing. So let's say a few more words with better chalk about Fourier analysis. Not better chalk. All right, so and I'm gonna couch this in what we know from wave mechanics. So what we have is that for states, the set of eigenkets, the positioning state, are complete orthonormal bases. Right? So that is to say, I can have a resolution of the identity integrating over all of these guys or all of these guys. Right? Moreover, x and x prime, they're orthogonal. P and P prime are orthogonal. We have a representation of one guy in terms of the other. We have the duality, we have this, because of this, we have that delta x minus x prime is, or I can say a delta function is the Fourier transform of the plane waves. So there's a duality between the delta functions and the plane waves. Okay? So from this, of course, what we have is we can write an arbitrary state as in a representation in position, for example. We can write it, we can write the state in terms of the position space, or we can write the state in terms of the momentum space. All right, so with that said, we want to translate that now, not in terms of representations of vectors in phase space. We want to look at the representation of operators in phase space. So we go from operators to super operators. No. So, what do I mean by that? Well, so instead of having a basis of states, we're looking to look at something that looks like a basis of operators. So in the same way that the plane waves are a basis of states, the displacement operators are a basis of operators. What do I mean by that? That means that I can project an operator onto this thing. It's got some amount of that, and then add them all up. That's what I did over here, right? I said that, you know, the state, I can project it onto the plane wave, and then the total state is just add up with those coefficients, those things. So the claim, which you will see in your homework, is that the set, this is not symmetric, this is just the set, okay, is a complete orthonormal set of operators. What do I mean by that? That means that any operator can be expanded in terms of these guys, just like I can expand any function in terms of plane waves. What does it mean to be orthogonal? Well, so we need an inner product. And the inner product is borrowed from matrix algebra. It's the trace inner product. So we're going to look at, this is where the super part of the super operator goes. So here, with my curvy brackets, is the inner product between two operators. And that inner product is defined to be the trace of A dagger with B. I don't know, this has some names, like Frobenius, I don't know which one this is, but it's some inner product. It's the anyway, the one that comes from matrices. It's simple.
I think that's the Hilbert-Schmidt.
Yeah, maybe that's it. Yeah, thanks. Thanks. I don't know.
Details.
Mathematicians love to throw around, it's the name, it's the Frobenius norm, because if you don't know what the Frobenius norm is, then you're just not smart. Drive me up the wall. It's just arguing by authority, by giving something a name that no one can remember except the people who know the name. All right, diatribe number 3 for the day. Continuing on. So that's my inner product, and so the claim is the following. The inner product between two of these plane wavy things is in the same way that the inner product between two real plane waves is a delta function. This is a delta function in phase space. So this is equal to alpha minus beta. Actually, there's a pi in there. Okay, that's something you will prove. And that inner product is just a shorthand for the trace of the D dagger alpha D beta. All right, so they're orthogonal and they're complete. What do I mean by complete? Well, what it means is that I can write in the same way that we just did this. We're going to project an arbitrary operator onto one of these plane waves and then add it up by just multiplying the projection onto the plane wave. So the claim is that the integral of the superoperator outer product is 1. This is kind of the measure of phase space. This is like the complete set, but now of operators rather than kets. They're super kets. Okay? So that means that if I wanted to say what is the ket A, well, that's that, which is just Fourier's theorem in operator land, because this is the projection of the thing onto the plane wave, and this is how much plane wave you got. So this is just a very fancy Frobenius-like way of writing. And this is kind of the whole story in quasi-probability distribution here. It's really the whole thing is here. One of these guys has got to be a dagger. Okay? That's this. Yeah?
So I guess using this picture, I mean, does that mean that we could define kind of rigorously like a super operator that took us from some operator in, normal form, say, to some operator in symmetric
That's
form?
what we're about to do.
Okay.
Yeah,
Cool.
that's exactly what it's about.
Okay. Sweet.
I should say that what is often written for reasons related to the characteristic function, because it doesn't matter if I change alpha to minus alpha here. So I'm integrating over the whole plane. And so often you look at it's written this way. And that's the way we're going to write it. So I'm sorry to use pen, but don't use pen.
Why? Why is it just turns out to be more convenient?
It's more convenient, right? Because remember we had rho. We had this. If A was rho, guess what this is? It's the characteristic function. So, indeed, what we have here, oh, so the other thing we have, so in the Fourier analysis was about the duality between plane waves and delta functions, right? If you took the Fourier transform of the plane wave, you got a delta function. So what is the Fourier transform and of course the Fourier transform is this. That's the Fourier transform. That's a, what is that operator? Well, that's going to be for you to show in homework that this is the symmetrically ordered delta function. In other words, this is, if I looked at this in X and P land, that this is equal to delta X minus X hat P minus P hat plus delta, let me write it better. Yes, sir.
On the top line, that right-hand side should be instead of alpha beta. Because you're integrating over that.
Right, right. Yeah, let's integrate over beta. Thank you. So that's the deal. The Fourier transform of a plane wave is a delta function. And since this was the symmetrically ordered guy, what you get is a symmetrically ordered guy. If I were, for example, to do this integral with v plus 1, and I will put the right dummy variable in there, what I would get is the delta function alpha delta alpha. No, one of these guys. Normally ordered. Okay, so we're out of time for now, but where we're going to go with this is the following. As we said, when this is rho, then this is the characteristic function. And the Fourier transform of the characteristic function is related to the quasi-probability distribution. And then, of course, if I wanted to find the trace of some observable O with that, well, that's going to be the trace of the observable with that. So I'm going to have the representation of the observable in phase space integrated with the distribution function, just as we wanted in the classical theory. Voila. Enjoy your evening.